Picture this. You're staring at a glass of water. Simple, right? But here's what'll blow your mind. The water you're drinking right now, there's a 100% chance that at least one molecule of it passed through a dinosaur. And that's just the beginning of how little we actually know about literally everything around us. So you think you know things. You think the world makes sense. You wake up, you see colors, you drink water, you go about your day. But what if I told you that the color blue you see might be completely different from the color blue I see? What if I told you that we've only explored about 5% of Earth's oceans and have no idea what's lurking in the other 95%? What if everything you thought you knew was actually just a guess? Here's the thing. We live in an age where we can send messages across the world in milliseconds, where we can edit genes, where we can land robots on Mars. We act like we've figured it all out, but the uncomfortable truth is this: we don't know anything. And I mean that literally. The more we learn, the more we realize how much we don't know. It's like opening a door only to find 100 more doors behind it, each one leading to questions we can't answer. And I'll be honest with you, this scares me sometimes. I spent most of my life thinking that if I just learned enough, read enough books, watched enough documentaries, I'd eventually understand how the world works. But the deeper I went, the more I realized that the smartest people in the world, the physicists, the neuroscientists, the philosophers, they're all essentially saying the same thing. We're all just guessing. Some guesses are better than others, sure, but at the end of the day, we're all stumbling around in the dark trying to make sense of a universe that might be fundamentally unknowable. But stick with me, because what I'm about to show you will completely change how you see the world, and by the end, you'll understand why the most honest answer to almost any question is actually, we don't know. Let me start with something simple, something you do every single day without thinking about it: yawning. Why do we yawn? You'd think after thousands of years of human existence we'd have this figured out, but we don't. Sure, there are theories. Some scientists say it's to cool down the brain. Others say it's to increase oxygen. But here's the kicker. None of these theories fully explain why yawning is contagious. You can be in a room full of strangers, someone yawns, and suddenly you're yawning too. Why? We just don't know. I tested this once. I was in a completely silent library, studying for an exam I was definitely going to fail, when someone 3 tables away yawned. Within 30 seconds, I counted 7 people yawning, including me. We were all strangers. None of us were tired at the same time. There was no logical reason for this chain reaction, but it happened anyway. And it gets weirder. Why do we laugh? Why do we cry? These seem like such basic human things, right? But we can't fully explain them. We cry when we're sad, sure, but we also cry when we're happy. We cry at weddings and funerals. We cry when we're overwhelmed with joy and when we're in pain. Scientists think crying might be a way for our body to process emotions, but that doesn't explain why we associate it with sadness when it happens in so many different contexts. Laughter is just as confusing. For a long time, people thought laughter was uniquely human, a social tool we evolved to show each other we're having a good time. But then we found out that dolphins laugh, rats laugh, other animals that aren't even primates can laugh. So what's the real reason? Nobody knows. Let's talk about something even more basic. Why are some people right-handed and others left-handed? Wouldn't it make more sense if everyone was ambidextrous? Like, from an evolutionary standpoint, being able to use both hands equally well seems like it would be a massive advantage. But instead, about 90% of people are right-handed, 10% are left-handed, and true ambidexterity is incredibly rare. Why? We have theories about brain lateralization and genetics, but no definitive answer. And here's what's really strange. Lefties have been discriminated against throughout history. The word sinister literally comes from the Latin word for left. In many cultures, the left hand is considered unclean. Some schools used to force left-handed children to write with their right hands. Why would evolution maintain a trait that caused social stigma? What advantage does left-handedness provide? We still don't know. But these mysteries are just the surface. Wait until you hear about what we don't know about the very ground beneath our feet. Now, let's zoom out a bit. Let's talk about the planet we live on. You'd think, after living here for 300,000 years, we'd have Earth figured out. But we don't, not even close. Take coastlines, for example. How long is the coastline of the United States? Seems like a simple question, right? But here's the thing, we don't actually know. The answer depends on how you measure it. Coastlines curve and bend and have tiny crevices. If you measure every single little indentation, the length keeps growing. Different surveys give different answers because they all cut corners differently. There's no universal agreement on how to measure a coastline, which means we can't give you a definitive answer for how long any coastline is. This is called the coastline paradox, and it's absolutely wild when you think about it. The more precisely you try to measure something, the longer it becomes. It's like trying to measure the edge of a cloud. Where exactly does the cloud end and the air begin? At what point do you stop measuring the tiny water droplets? Think of it this way. Imagine you're trying to measure the border of a forest by walking around it. If you walk in a straight line between major landmarks, you might say the border is 10 miles. But if you follow every single tree, walking around each trunk, the distance could be 50 miles. If you measure around every branch, 500 miles. Every leaf? The number becomes astronomical. That's essentially what's happening with coastlines, except we can't even agree on whether we're measuring trees, branches, or leaves. Or here's another one. We've only explored 5 to 10% of Earth's oceans. The rest? Complete mystery. And when I say we've only explored 5%, I mean we've physically gone down there and looked around. We've mapped more of the surface of Mars than we have of our own ocean floor. Think about that for a second. We know more about a planet millions of miles away than we do about the water covering 71% of our own planet. And the stuff we have found down there, absolutely terrifying. Fish with transparent heads that let you see their brains. Fish with teeth so big they can't close their mouths. The bear-eye fish has a transparent dome for a head and tubular eyes that can rotate to look up or forward. The blobfish looks like a melting human face. And these are just the creatures we've discovered. The deeper you go, the weirder it gets. In 1977, scientists discovered hydrothermal vents on the ocean floor, underwater volcanoes essentially, and found entire ecosystems living around them in complete darkness. These creatures don't use photosynthesis, they use chemosynthesis, getting energy from chemicals instead of sunlight. We didn't even know this was possible until we found it. What else is down there that we can't even imagine? Which makes you wonder, what's in that other 90% we haven't explored? And why haven't we explored it? The answer is simple. The ocean is hostile to human life in ways that space isn't. The pressure at the deepest parts of the ocean would crush a human instantly. The Marianas Trench is almost 7 miles deep. If you put Mount Everest at the bottom of the Marianas Trench, there would still be over a mile of water above its peak. But it's not just the oceans, it's life itself. And the question of what life actually is will make your head spin. What is life? I know that sounds like a pretentious philosophy question, but it's actually a real scientific problem. We can tell the difference between a living thing and a non-living thing. A cat is alive, a rock is not. Simple, right? But when you try to define what life actually is, it gets messy real fast. Scientists say life has certain characteristics. It responds to stimuli, it metabolizes energy, it grows, it reproduces. But those are just things life does. They're not what life is. It's like trying to define a car by saying it moves and has wheels. That's what a car does, but it doesn't tell you what a car actually is. And then there's the question of where life came from. We have theories. We think life started in the ocean, probably near hydrothermal vents, where chemicals mixed in just the right way to create self-replicating molecules. But we don't actually know. We can't recreate it in a lab. We can't go back in time and watch it happen. It's all educated guesswork. Here's where it gets really wild. We share 50% of our DNA with bananas. Not a typo, bananas. We're literally half banana. We also share about 60% of our DNA with fruit flies, which raises an interesting question. If we're so similar genetically to these other organisms, what actually makes us human? For a long time, the answer was tools. Humans use tools, and that's what makes us special. Except we found out that chimpanzees use tools too. They use sticks to get termites out of holes. They use rocks to crack open nuts. They even use leaves as makeshift umbrellas. So tools aren't unique to humans. Okay, fine. Maybe it's emotions. Humans have complex emotions that other animals don't have. Except chimpanzees have emotions too. They mourn their dead, they have long-lasting family bonds, they show empathy. They even have what looks like a sense of humor. Jane Goodall observed chimps playing with each other just for fun. No survival benefit, just pure enjoyment. She watched a young chimp sneak up behind an older chimp and tickle them, then run away laughing. This wasn't food-motivated behavior. This wasn't territorial. This was just messing with someone for the fun of it. Sound familiar? So maybe it's consciousness, self-awareness, the ability to think about thinking. Except we've done studies where we put animals in front of mirrors to see if they recognize themselves, and a lot of them do. Dolphins recognize themselves. Elephants recognize themselves. Even some birds recognize themselves. Magpies will use mirrors to remove marks from their own bodies, something that requires understanding that the reflection is yourself. In 2012, a group of neuroscientists signed something called the Cambridge Declaration on Consciousness, which basically said that humans aren't the only conscious animals. Tons of animals have the brain structures necessary for consciousness. The declaration explicitly stated that the weight of evidence indicates that humans are not unique in possessing the neurological substrates that generate consciousness. So what makes us human? We don't know. We keep moving the goalposts. Every time we think we found something unique about humans, we discover that other animals can do it too. Maybe the only thing that makes us unique is our ability to ask the question, what makes us unique? But even that might not be true. We just can't know what questions other animals are asking themselves. But if you think the mystery of what makes us human is complicated, wait until you hear about the mystery of what's out there in space. The universe and the great silence. Let's talk about the universe, because if you thought Earth was confusing, space is on another level entirely. We know the universe is big, really big, so big that our brains can't actually comprehend it. There are hundreds of billions of galaxies, each with hundreds of billions of stars, and many of those stars have planets orbiting around them. Let me put this in perspective. If you wanted to count every star in just our galaxy, the Milky Way, and you counted one star per second, it would take you over 3,000 years. And that's just one galaxy. There are hundreds of billions of galaxies. The numbers become meaningless at that scale. Which brings us to one of the biggest questions in science. Are we alone? With all those billions and billions of planets out there, what are the odds that Earth is the only one with life? Statistically, it seems impossible. There should be millions, maybe billions of planets with life. And some of that life should be intelligent. Some of it should be way more advanced than us. So where is everybody? This is called the Fermi paradox, named after physicist Enrico Fermi, who asked this exact question at a lunch conversation in 1950. The story goes that Fermi and his colleagues were discussing UFO sightings and the possibility of interstellar travel when Fermi suddenly asked, "But where is everybody?" His point was simple. If intelligent life is common, and if even a tiny fraction of civilizations develop the technology to explore space, the galaxy should be teeming with evidence of alien civilizations. But we see nothing. We hear nothing. The silence is deafening. There are a bunch of possible answers. Maybe aliens exist, but they're too far away. Space is so unimaginably huge that even traveling at the speed of light, it would take millions of years to reach other galaxies. Our earliest radio signals, the ones we sent out over 100 years ago, have only traveled about 100 light years.
That's nothing in cosmic terms. That's like shouting into the Grand Canyon and expecting someone in New York to hear you. If there's intelligent life 1,000 light years away, our signals haven't even reached them yet. Or maybe aliens exist, but they're not interested in us. Think about ants. You probably walk past millions of ants in your lifetime without giving them a second thought. To a sufficiently advanced alien civilization, we might be the ants, not worth contacting. We might be as interesting to them as bacteria in a petri dish are to us. Carl Sagan once said that we're like a newborn baby in a nursery, crying out and wondering why no one in the rest of the house is coming to see us. Maybe they hear us. Maybe they just don't care. Or maybe, and this is the scary one, maybe there's something called the Great Filter. The idea is that there's some kind of hurdle in the evolution of intelligent life that most civilizations don't survive. Maybe it's nuclear war. Maybe it's climate change going rogue. Maybe it's something we can't even imagine. Whatever it is, most civilizations hit this filter and go extinct before they can reach out to the stars. The terrifying part is we don't know if we've already passed the Great Filter or if it's still ahead of us. Maybe we exist because we got lucky and survived something that killed everyone else. Maybe the Great Filter was the jump from simple single-celled life to complex multicellular life, which took billions of years on Earth and might be incredibly rare. Or maybe we're about to hit it. Maybe every civilization eventually develops nuclear weapons and destroys themselves. Maybe every civilization eventually creates AI that wipes them out. Maybe there's some cosmic threat we don't even know about yet. The universe might be filled with the ruins of dead civilizations that didn't make it. But there's another possibility, though, and it's even darker. It's called the dark forest hypothesis. Imagine the universe is like a dark forest. Every civilization is a hunter moving through the forest with a gun. You don't know if the other hunters are friendly or hostile. You don't know if calling out will attract friends or predators. The safest strategy is to stay silent and hidden. And if you do detect another civilization, the safest thing to do is to destroy them before they destroy you. In this scenario, the universe is full of civilizations, but they're all hiding from each other. Making noise, sending out radio signals, trying to contact other civilizations, that's suicidal. It's like turning on a flashlight in a dark forest full of armed strangers. Maybe the civilizations that survive are the ones that stay quiet. Maybe Earth's constant radio broadcasts are the equivalent of a baby screaming in a dark forest, and we just haven't attracted the wrong kind of attention yet.
And speaking of things we're not looking for properly, let me tell you about what the universe is actually made of. You'd think we'd have this one figured out, right? We've been studying physics for centuries. We have particle accelerators, we have space telescopes, but here's the truth. We only understand about 5% of the universe. The other 95%? Complete mystery. Scientists call it dark matter and dark energy. We can see their effects. Galaxies are held together by gravity from matter we can't detect, and the universe is expanding at an accelerating rate because of some kind of energy we don't understand. But we have no idea what dark matter or dark energy actually are. We've given them names, but that doesn't mean we understand them. It's like if you saw a car driving down the street with no visible driver and you said, "Must be a ghost driver," and then just moved on with your life. You've named it, but you haven't explained it. That's where we are with 95% of the universe. We've named it, we can measure some of its effects, but we have absolutely no idea what it is. Think about how absurd this is. Imagine you're a doctor and a patient comes in complaining about pain. You examine them and determine that you understand about 5% of what's happening in their body. The other 95%? Mystery. You can see that something is affecting their organs, you can measure some of the symptoms, but you have no idea what's causing it or what it's made of. That's humanity's understanding of the universe right now. And it gets worse. We don't know if the universe is infinite or finite. We can only see a certain portion of it, the observable universe, because light from farther away hasn't had time to reach us yet. But we don't know if there's an edge to the universe or if it just keeps going forever. Both possibilities are equally mind-bending. We don't know what happened before the Big Bang.
We can trace the universe back to a fraction of a second after the Big Bang, but we can't see earlier than that. And the question, what happened before time, might not even make sense, because time itself might have started with the Big Bang. Asking what came before time is like asking what's north of the North Pole. The question itself might be incoherent. We don't know if our universe is the only universe. The multiverse theory suggests there might be an infinite number of universes, each with different physical laws. In some universes, gravity might be stronger. In others, the speed of light might be different. In some universes, stars might never have formed. In others, life might be everywhere. But we have no way to test this. We can't see other universes or interact with them. It might be true, but we'll never know. Here's something that really messed me up when I first learned about it. We don't know if the laws of physics are the same everywhere in the universe. We assume they are, but we can't check. Maybe there are parts of the universe where gravity works differently or where light behaves strangely. We have no way to know. We're making a huge assumption based on very limited data, the tiny corner of one galaxy that we've been able to examine. And you know what the craziest part is? Even the 5% we think we understand might be wrong. Everything I just told you about physics and the universe is based on our current best theories. But theories change. They get replaced. In the 1800s, physicists thought we had basically figured out how the universe worked. There were just a few minor details to work out, a few decimal places to nail down. Then we discovered radioactivity, quantum mechanics, and relativity, and realized we didn't understand anything. The entire foundation of physics had to be rebuilt from scratch. What if we are in the same position right now? What if our current understanding of physics is like a beautifully detailed map of a place that doesn't actually exist? We might be spending billions of dollars building particle accelerators and space telescopes to test theories that are fundamentally wrong. But speaking of things that are fundamentally confusing, let's talk about something even more basic than the universe. Let's talk about you. Let's bring it back down to Earth for a second. Let's talk about something that affects every single one of us every single day. Time. What is time? You're probably thinking, that's a stupid question. Everyone knows what time is. But do you? Try to define it without using the word time or any synonyms. You can't, can you? We all experience time, we all feel it passing, but we can't define what it actually is. Is it a physical thing? Is it just a human construct? We invented clocks to measure time, but did we discover time or invent it? And here's an even weirder question. Does time actually flow forward, or is that just how we perceive it? In physics, most equations work the same whether time is moving forward or backward. The laws of physics don't really care which direction time is going. But we experience time as moving in one direction. We remember the past, but not the future. We can affect the future, but not the past. Why? Nobody knows. Some physicists think time might not be fundamental at all. It might be an emergent property of something more basic, the way temperature emerges from the movement of molecules. You can't point to a single molecule and say, that one has temperature. Temperature only exists when you have lots of molecules moving around. Maybe time is the same way. Maybe it only exists at large scales, and at the quantum level, there's no such thing as time. And while we're on the topic of things we experience every day without understanding them, let's talk about sleep. You spend about a third of your life asleep. You'd think we'd understand why. But we don't. Not really. We know what happens when you don't sleep. You feel terrible, your cognitive function declines, you eventually hallucinate, and if you stay awake long enough, you die. But we don't know why sleep is necessary in the first place. Some scientists think sleep is when your brain cleans itself, flushing out toxins that built up during the day through something called the glymphatic system. Others think it's when your brain processes memories and consolidates learning. But these are just theories. We don't have a complete understanding of why we need to spend a third of our lives unconscious. And dreams? Forget about it. We have no idea why we dream. Freud thought dreams were about repressed desires, but most modern scientists think Freud was just making stuff up. Jung thought they were about archetypes and the collective unconscious, which sounds deep but doesn't actually explain anything. Modern neuroscientists think dreams might be your brain's way of processing information or running simulations. Some think dreams are just random noise, your brain's screensaver while it does maintenance. But that doesn't explain why dreams often have coherent narratives, why they sometimes help us solve problems, or why we sometimes have recurring dreams. We spend hours every night in these vivid, bizarre, often nonsensical experiences, and we can't explain why. I once had a dream where I could fly, but only if I held my breath. The moment I breathed, I would fall. In the dream, this made perfect sense. I spent the whole dream trying to fly to different places while managing my breathing. When I woke up, I tried to figure out what it meant. Was my subconscious trying to tell me something about control, about freedom and its limitations? Or was my brain just randomly firing neurons and creating a nonsensical story? I'll never know. Nobody will. Let's talk about something that sounds simple but is actually incredibly complex. How your brain works. You have about 86 billion neurons in your brain, each connected to thousands of other neurons. These neurons communicate through electrical and chemical signals, creating unimaginably complex networks. But here's what we don't know. How does all of that create consciousness? How do electrical impulses in your brain become the feeling of being you? This is called the hard problem of consciousness, and it's one of the biggest unsolved questions in neuroscience and philosophy. You can map every neuron in the brain, you can track every signal, but you still can't explain why those signals create subjective experience. Why does seeing the color red feel like something? Why does pain hurt? How does the physical stuff in your brain create the mental experience of being alive? Some scientists think consciousness is an emergent property. It arises from the complexity of neural networks in the same way that wetness emerges from water molecules. Individual water molecules aren't wet. Wetness only exists when you have lots of water molecules together. Maybe consciousness is the same way. But that doesn't really explain it. It just pushes the question back a step. Why does complexity create consciousness? Why doesn't a sufficiently complex computer have subjective experiences? Others think consciousness might be fundamental to the universe, like space or time or energy, that it's not created by brains, but somehow exists as a basic property of reality. This is called panpsychism, and while it sounds crazy, some serious scientists and philosophers take it seriously. But we have no way to test this. We can't even agree on what consciousness is, let alone where it comes from. And here's another fun one. Do we have free will? You probably think you do. You make choices every day. You decide what to eat, what to wear, what to do. But do you really? Or is every decision you make just the result of prior causes? Your genetics, your upbringing, the exact state of every neuron in your brain at that moment. Neuroscientists have done experiments where they can predict what choice you're going to make before you're consciously aware of making it. They can see activity in your brain that indicates you're about to move your hand several seconds before you actually decide to move it. Which raises a disturbing question. If your brain has already decided before you're aware of it, are you really making a choice? Benjamin Libet did the famous experiment in the 1980s. He asked people to move their hand whenever they felt like it and note the time they decided to move. Meanwhile, he monitored their brain activity. He found that the brain showed signs of preparing to move about half a second before the person reported deciding to move. The decision was already happening before they were conscious of it. Some philosophers argue that free will is an illusion, that everything you do is determined by prior causes, even if it feels like you're making free choices. Others argue that free will exists, but in a more limited way than we think. And others say the whole question is confused and we're asking the wrong thing. The point is, we don't know. You might not even have free will, and there's no way to prove it either way. And if you think that's unsettling, wait until I tell you about how little we actually know about knowing itself.
Let's talk about knowledge itself. How do you know anything? This sounds like a pretentious philosophy question, but stick with me because it gets weird. You probably think you know things because you can see them or touch them or measure them. But here's the problem. All of that information comes to you through your senses, and your senses can be wrong. You've seen optical illusions, you've heard audio that sounds like two different words depending on what you're expecting to hear, like the famous Yanni or Laurel debate. Your senses are constantly being fooled, so how do you know that anything you perceive is actually real? René Descartes, the famous philosopher, tried to find something he could know for certain. He doubted everything. He said maybe your senses are lying to you. Maybe you're dreaming right now. Maybe there's an evil demon feeding you false information about reality, like you're in the Matrix. He doubted everything until he arrived at one thing he couldn't doubt. I think, therefore I am. If he could doubt, he must exist to do the doubting. But later philosophers pointed out that even this isn't certain. Just because there are thoughts doesn't mean there's a thinker. Maybe there are just thoughts happening, no you required. Friedrich Nietzsche argued this exact point. He said when we say I think, we're already assuming there's an I doing the thinking, but that's not proven. Maybe thinking just happens and we incorrectly attribute it to a self. So we can't even prove for certain that we exist. Everything else is just layers of assumptions on top of that shaky foundation. We assume our senses are generally reliable. We assume the external world exists. We assume other people are conscious. We assume the laws of logic are valid. But these are all assumptions. We can't prove any of them with certainty. And if you think science will save us here, think again. Science is amazing. It's given us technology, medicine, and understanding of the natural world. But science can never be 100% certain about anything. When scientists at CERN announced they'd discovered the Higgs boson in 2012, they didn't say we found it for sure. They said they had 5 sigma certainty, which means there's about a 1 in 3.5 million chance they're wrong. 1 in 3.5 million sounds pretty good, right? Except in 2011, CERN ran an experiment that had 6 sigma certainty, 1 in a half billion chance of being wrong, that showed particles traveling faster than light. This should have been impossible. It would have broken physics as we know it. Entire physics departments started writing papers about the implications, and it turned out to be wrong. Later experiments couldn't replicate it. It was a fluke caused by a loose fiber optic cable. The point is, science deals in probabilities, not certainties. Every scientific theory could potentially be proven wrong tomorrow. We used to think the Earth was the center of the universe. We used to think the sun revolved around the Earth. We used to think bloodletting cured diseases. We used to think the universe was static and eternal. We were wrong about all of it. How many things do we believe now that future generations will look back on and laugh at? Maybe chemotherapy will seem as barbaric as bloodletting seems to us. Maybe our understanding of quantum mechanics is completely wrong. Maybe consciousness isn't produced by the brain at all. We don't know what we don't know. But let me tell you about some specific everyday things that will make you question everything. Let's talk about some more everyday stuff we can't explain. Why is yawning contagious? Seriously, we have theories, but we don't actually know. You can be in a room with strangers, see someone yawn, and suddenly you're yawning too. Why? Some scientists think it's related to empathy and mirror neurons, parts of your brain that activate when you see someone else doing something. But that doesn't explain why you yawn when you see a stranger yawn, or why you sometimes yawn when you just read the word yawn. Speaking of which, you're probably yawning right now. Sorry about that. I yawned 3 times writing this section. Why do we have fingerprints? You'd think there would be an obvious evolutionary advantage, but we're not really sure what it is. Some scientists think fingerprints help us grip things better by channeling water away from our fingers, like tire treads in rain. Others think they might help with our sense of touch by amplifying vibrations. We don't know for sure. And yet every single human has a unique fingerprint pattern. Why? What purpose does the uniqueness serve? Why do we get goosebumps? The leading theory is that it's a vestigial response from when our ancestors had more body hair. When you're cold or scared, your hair stands up to trap air and keep you warm, or make you look bigger to predators. But we don't have enough body hair for this to work anymore, so we just get goosebumps. But that's just a theory, and it doesn't explain why we sometimes get goosebumps from music or emotional moments. Why does music give us chills? You know that feeling when a song hits just right and you get shivers down your spine? We don't fully understand why that happens. It seems to be related to dopamine release in the brain, but we don't know why music would trigger that response in the first place. Music doesn't help us survive. It doesn't provide calories or shelter or protection from predators. So why does it affect us so deeply? Every culture in human history has had music. We found ancient flutes made from bone that are over 40,000 years old. Music is universal to humanity, but we don't know why. Some anthropologists think it might have helped our ancestors bond as groups, turning individuals into a unified tribe. Others think it might be a byproduct of language processing. We don't know. Why do we have different blood types? A, B, AB, O, positive, negative. We know these blood types exist, and we know they matter for transfusions, but we don't know why humans have different blood types at all. What's the evolutionary advantage? Some blood types are more common in areas where certain diseases are prevalent, suggesting blood type might provide some protection against diseases, but we're not sure. Why do some people have allergies and others don't? Why are allergies becoming more common? We have theories. Maybe our modern environments are too clean, so our immune systems overreact to harmless things. This is called the hygiene hypothesis. But we don't know for sure. Some people are deathly allergic to peanuts while others eat them by the handful. Some people's immune systems treat pollen like a deadly invader while others don't react at all. Why? We don't fully understand. Why do placebos work? This is a big one. If you give someone a sugar pill and tell them it's medicine, there's a decent chance they'll actually feel better. Their symptoms might improve. In some cases, their body might actually heal. We call this the placebo effect, but naming it doesn't mean we understand it. How can your brain heal your body just because you think you're getting treatment? And here's where it gets weirder. There's something called the nocebo effect, which is the opposite. If you tell someone a harmless pill will make them sick, they might actually get sick. Your brain can apparently make you sick just by believing you should be sick. In clinical trials, people in the placebo group sometimes experience the exact side effects they were warned about, even though they're taking sugar pills. Even more bizarre, there's something called the open-label placebo effect. Researchers have done studies where they tell people, this is a placebo, it contains no active ingredients, and people still feel better. Just the ritual of taking a pill, even when you know it's fake, can have therapeutic effects. How is that possible? We don't know. Why do we get hiccups? Hiccups are involuntary spasms of the diaphragm. But why do they happen? There's no clear evolutionary purpose. Some people think it might be a leftover reflex from when our ancestors were amphibians. Tadpoles use a similar reflex to breathe through gills. But that's just speculation. And we definitely don't know why holding your breath or drinking water upside down sometimes stops hiccups. Why does hot water freeze faster than cold water sometimes? This is called the Mpemba effect, named after a Tanzanian student named Erasto Mpemba who noticed it in the 1960s. You'd think cold water would freeze faster since it has less heat to lose, but under certain conditions, hot water freezes first. Scientists have proposed various explanations. Maybe hot water evaporates more, reducing the amount that needs to freeze. Maybe convection currents in hot water help it freeze faster. Maybe dissolved gases in water affect freezing. But we don't have a definitive answer. And think about how absurd that is. Freezing water, one of the most basic things you can do in a kitchen. We don't fully understand it. But if you think the mysteries of everyday life are strange, wait until you hear about the things we've lost and will never get back.
Let's talk about some historical stuff we don't know. We don't know who built Stonehenge or why. We have theories. Maybe it was a religious site, maybe it was an astronomical calendar, maybe it was a burial ground. The stones align with the summer and winter solstices, suggesting astronomical knowledge. But we don't know for sure. And we definitely don't know how ancient people moved those massive stones without modern technology. The largest stones at Stonehenge weigh about 25 tons. They were transported from quarries about 20 miles away. That's hard enough with trucks and cranes. How did people 5,000 years ago do it? We've tried to recreate it with period-appropriate tools and methods. The best we can do is slowly drag the stones on wooden rollers. It would have taken hundreds of people and months of work to move a single stone, but we're not even sure that's how they did it. We don't know how the pyramids were built. We have theories about ramps and levers and thousands of workers, but we don't have definitive proof, and some of the precision in the pyramids is hard to explain even with our theories. The blocks fit together so perfectly that you can't slide a piece of paper between them. The pyramid is aligned almost perfectly with true north, with an error of less than 1/15 of a degree. How did they achieve that precision? The Great Pyramid of Giza contains about 2.3 million stone blocks, each weighing between 2.5 and 15 tons. It was built in about 20 years. That means workers would have had to place a block every 2 minutes, working 10 hours a day, every day, for 20 years. How is that possible? We don't know. We don't know what happened to the Library of Alexandria. We know it burned down, but we don't know exactly when or who was responsible. Some people blame Julius Caesar. He set fire to enemy ships in the harbor in 48 BC, and the fire spread to the city. Others blame later conquerors and religious zealots who destroyed pagan knowledge. It probably wasn't one big fire, but multiple incidents over time. But we'll never know for sure. And we'll definitely never know what knowledge was lost. Ancient texts, scientific discoveries, philosophical works, all gone. The library supposedly held over 500,000 scrolls. It was the greatest repository of knowledge in the ancient world. What mathematical theorems were proven there and then lost? What medical knowledge? What engineering techniques? What literature? We'll never know. This is what really gets me. It's not just that we don't know things about the present. We don't even know what we used to know. Human knowledge isn't a constantly increasing line, it's a jagged mess with huge chunks missing. The ancient Romans had concrete that was stronger than modern concrete. We only recently figured out how they made it. The ancient Greeks had a computer, the Antikythera mechanism, that we can't fully explain. How did they make it? What else could they make? We don't know if the Voynich manuscript is real or a hoax. It's a book written in a completely unknown language or code filled with bizarre illustrations of plants that don't exist and astronomical diagrams that don't make sense. People have been trying to decode it for centuries. Carbon dating shows it was made in the early 15th century. The illustrations are detailed and purposeful, suggesting it means something. But what? Is it a lost language, an elaborate code, medical knowledge, or just nonsense designed to fool people? We don't know. Some of the best cryptographers in the world have tried to crack it. The NSA tried. Computer algorithms have tried. Nothing works. Either it's an incredibly sophisticated code that's beyond our ability to break, or it's gibberish that just happens to have statistical properties that look like language. We may never know. But here's the really unsettling part. These are things we know we don't know. We know the Library of Alexandria burned. We know the Voynich manuscript exists. What about all the things we don't even know we don't know?
Let's talk about Earth's history. We don't know what killed the dinosaurs. Okay, we're pretty sure it was an asteroid impact about 66 million years ago. There's a layer of iridium in the geological record worldwide from that time, and iridium is rare on Earth but common in asteroids. There's also a massive impact crater off the coast of Mexico that dates to the right time. But we're not 100% certain. And even if it was an asteroid, we don't know all the details of how it led to mass extinction. Did the dinosaurs die quickly or slowly? How did anything survive? Why did some species make it while others didn't? We have theories. Maybe the impact threw up so much dust that it blocked out the sun, causing a global winter. Plants died, herbivores starved, carnivores starved. But this is speculation based on limited evidence. We weren't there. We can't rewind time and watch it happen. We don't know how many mass extinctions there have been. We know about the Big Five, but there might have been others. And we don't know what caused all of them. The Permian extinction, the worst one, killed about 96% of all species. What caused it? Maybe volcanic eruptions in Siberia. Maybe an asteroid. Maybe both. We don't know. We don't know how life on Earth began. We think it started in the ocean about 3.5 to 4 billion years ago, probably near hydrothermal vents where heat and chemicals from the Earth's interior mix with ocean water. But we can't recreate it in a lab. We don't know exactly what conditions were necessary or exactly what chemicals were involved. Scientists have created amino acids, the building blocks of life, in the lab by simulating early Earth conditions, but that's a long way from creating life. We don't know how those amino acids assembled into proteins, how proteins assembled into cells, how cells learned to replicate. The jump from chemistry to biology is still a mystery. We don't know if there were any civilizations before ours.
This sounds crazy, but think about it. If there was an industrial civilization 100 million years ago, would we even know? Fossils are rare. Most things don't fossilize. Buildings would erode, technology would corrode. After enough time, there might be no trace left. Scientists have looked for evidence of pre-human civilizations. They call it the Silurian hypothesis, named after a Doctor Who episode. They're looking for things that would leave a permanent mark in the geological record. Plastic would leave a signature, nuclear waste would leave a signature, massive changes in carbon dioxide levels would leave a signature, and we haven't found anything like that. But absence of evidence isn't evidence of absence. A civilization that lasted 100,000 years, 500 times longer than our industrial civilization, might not leave enough traces to be detectable millions of years later. And that's terrifying to think about. What if this isn't humanity's first attempt? What if there have been other species that rose to intelligence, built civilizations, and then went extinct, and we'll never know they existed? But the mysteries of the past pale in comparison to the mysteries of right now, in your own body. Let's talk about the human body, because there's so much about our own bodies we don't understand. We don't know why we need to sleep. We know what happens if you don't sleep, you die, but we don't know why sleep is necessary. Is it for memory consolidation, brain cleaning, energy conservation? Probably all of the above, but we're not sure. The longest anyone has stayed awake in a documented, observed experiment is 11 days. Randy Gardner did it in 1964 as a high school science project. By the end, he couldn't concentrate. He had memory problems. He hallucinated. His speech was slurred. But he recovered completely after sleeping. However, there are fatal diseases where people lose the ability to sleep. Fatal familial insomnia, and they die within months. Why does lack of sleep kill you? We don't know the exact mechanism. We don't know why we age. We know we do age. Our cells stop dividing as efficiently, our telomeres get shorter, our DNA accumulates damage. But we don't know why this happens. Is it programmed into us? Is it just accumulated wear and tear? Could we theoretically stop aging if we understood it better? Some animals barely age. There's a jellyfish that can essentially live forever by reverting to its juvenile form. There's a fish called the rough-eye rockfish that can live over 200 years. There are trees that are thousands of years old. Why do these organisms not age the way we do? What's different about them? If we understood it, could we apply it to humans? We don't know how memories work. We know they involve neural connections in the brain, but we don't know how a memory is actually stored or retrieved. Can you pinpoint exactly where a specific memory is in the brain? No. It's distributed somehow across networks of neurons, but we don't understand the mechanism. Your brain has about 86 billion neurons, each connected to thousands of others, creating trillions of connections. Somewhere in that network is every memory you have. Your first day of school, what you had for breakfast, the face of everyone you've ever met. But we can't find them. We can't see a memory in a brain scan. We don't know how the physical structure of neurons encodes the subjective experience of remembering. We don't know how anesthesia works. This is a big one. We use anesthesia all the time in surgeries. We can put people to sleep reliably, but we don't actually understand how it works. We know which drugs do it, but we don't know the mechanism of how they make you unconscious. That's insane when you think about it. One of the most important tools in modern medicine, used millions of times a year, and we don't know how it works. Different anesthetics have different chemical structures and should work in different ways, but they all somehow produce unconsciousness. The only thing they have in common is that they're all fat-soluble. That's not much of a clue. It's like knowing that all cars have wheels but not understanding how engines work. We don't know why we have an appendix. It seems to be useless. People get it removed all the time and are fine. Some scientists think it might have been useful to our ancestors for digesting plants, but we're not sure. Others think it might serve as a reservoir for gut bacteria, a safe house where beneficial bacteria can hide when you have diarrhea and then repopulate your gut afterward. But mostly it just sits there and occasionally gets infected and tries to kill you. We don't know why some people are ticklish and others aren't. We don't know why you can't tickle yourself. We don't know why being tickled makes you laugh, even though it's not really enjoyable. The current theory is that tickling evolved as a way for parents and children to bond, teaching kids to protect vulnerable areas of their body. But that doesn't explain all of it. We don't know how the immune system distinguishes between your own cells and foreign invaders. We know it does, that's how it fights off infections, but the exact mechanism of how it learns to recognize self versus non-self is still partially mysterious. And sometimes it gets it wrong, which is how autoimmune diseases happen. Your immune system attacks your own body, thinking it's foreign. But if you think the human body is confusing, the universe is even worse.
Let's talk about the universe some more because it's full of unanswered questions. We don't know if the universe is infinite or finite. We can only see a certain portion of it, the observable universe, which is about 93 billion light-years across. That's as far as light has had time to travel since the Big Bang. But we don't know if there's an edge to the universe or if it just keeps going forever. Both possibilities are equally mind-bending. If the universe is finite, what's beyond the edge? If it's infinite, that means there are infinite planets, infinite galaxies, infinite versions of you reading this right now. Infinity is weird. If the universe is truly infinite, then everything that can happen will happen an infinite number of times. There are infinite Earths out there, infinite yous, some living lives almost identical to yours, some making different choices. We don't know what happened before the Big Bang. We can trace the universe back to a fraction of a second after the Big Bang, but we can't see earlier than that. And the question, what happened before the Big Bang, might not even make sense because time itself might have started with the Big Bang. Let's talk about the universe some more because it's full of unanswered questions. We don't know if the universe is infinite or finite. We can only see a certain portion of it, the observable universe, which is about 93 billion light-years across. That's as far as light has had time to travel since the Big Bang. But we don't know if there's an edge to the universe or if it just keeps going forever. Both possibilities are equally mind-bending. If the universe is finite, what's beyond the edge? If it's infinite, that means there are infinite planets, infinite galaxies, infinite versions of you reading this right now. Infinity is weird. If the universe is truly infinite, then everything that can happen will happen an infinite number of times. There are infinite Earths out there, infinite yous, some living lives almost identical to yours, some making different choices. We don't know what happened before the Big Bang. We can trace the universe back to a fraction of a second after the Big Bang, but we can't see earlier than that. And the question, what happened before the Big Bang, might not even make sense because time itself might have started with the Big Bang. Asking what came before time is like asking what's north of the North Pole. The question itself might be incoherent. Some physicists think time might be cyclical. The universe expands, then contracts in a big crunch, then bounces back in another Big Bang. This would mean our universe is just one in an infinite series. Others think our universe might have budded off from a parent universe. We have no way to test these ideas. We don't know if our universe is the only universe. The multiverse theory suggests there might be an infinite number of universes, each with different physical laws. In some universes, gravity might be stronger. In others, the speed of light might be different. In some universes, stars might never have formed. In others, life might be everywhere. But we have no way to test this. We can't see other universes or interact with them. It might be true, but we'll never know. The multiverse theory actually comes from taking quantum mechanics seriously. In quantum mechanics, particles exist in multiple states until observed. One interpretation, the many worlds interpretation, says that all possibilities actually happen, just in different universes. Every time a quantum event could go two ways, the universe splits into two universes, one for each outcome. If that's true, there are an uncountable number of universes being created every instant, but we have no way to prove it. We don't know what most of the universe is made of.
I mentioned this earlier, but it bears repeating. We understand about 5% of the universe. The other 95% is dark matter and dark energy, which we know exists because we can see their effects, but we have no idea what they actually are. Dark matter holds galaxies together. Galaxies spin so fast that they should fly apart, but they don't. Something is holding them together with gravity. We can't see this matter, it doesn't interact with light, but we can see its gravitational effects. We've looked for dark matter particles in the most sensitive detectors we can build, deep underground, shielded from cosmic rays. We haven't found anything yet. Dark energy is even weirder. The universe is expanding, and that expansion is accelerating. Something is pushing the universe apart, working against gravity. We call it dark energy, but we have no idea what it is. It makes up about 68% of the universe. Think about that. 2/3 of the universe is made of something we don't understand at all. We don't know if time travel is possible. The laws of physics don't explicitly forbid it, but we've never observed it. Einstein's equations actually allow for solutions where time travel is possible, things like wormholes and closed time-like curves. But we don't know if these solutions correspond to anything real. Maybe it's possible, but incredibly difficult. Maybe it's impossible. Maybe time doesn't work the way we think it does, and the whole question is nonsensical. The main problem with time travel is paradoxes. If you travel back in time and prevent your parents from meeting, you would never be born. But if you were never born, you couldn't travel back in time to prevent your parents from meeting. It's self-contradictory. Some physicists think this means time travel is impossible. Others think it means the universe would somehow prevent you from creating a paradox. Maybe your time machine would break, or you'd fail to prevent your parents from meeting. We don't know. We don't know if there are other dimensions beyond the 3 spatial dimensions and 1 time dimension we experience. String theory suggests there might be 10 or 11 dimensions, but most of them are curled up so small we can't perceive them. Imagine an ant walking on a wire. To the ant, the wire looks like a one-dimensional line, but actually the wire has a second dimension, the circumference around it. The ant could walk forward and backward, the long dimension, or circle around the wire, the curled-up dimension. Maybe we're like the ant, unable to perceive the extra dimensions that are curled up at incredibly tiny scales. But we can't test this. It's mathematically interesting, but we don't know if it's real. String theory has been around for decades and hasn't made any testable predictions yet. Some physicists think it's our best hope for a theory of everything. Others think it's a dead end, math that's beautiful but doesn't describe our universe. But if you think regular physics is confusing, quantum physics will really mess with your head.
Let's talk about quantum mechanics, because it's full of things we don't understand. We don't know why observing a particle changes its behavior. In quantum mechanics, particles exist in a superposition of states until they're measured. An electron can be spinning clockwise and counterclockwise at the same time. A photon can be in 2 places at once. The act of measurement collapses the superposition into one definite state. But why? How does the particle know it's being observed? We have no idea. This isn't a metaphor or simplification. This is really what happens. In the famous double-slit experiment, you shoot individual photons at a barrier with 2 slits. When you don't observe which slit the photon goes through, it acts like a wave and goes through both slits at once, creating an interference pattern. When you do observe which slit it goes through, it acts like a particle and goes through only one slit, creating a different pattern. The act of observation changes the result. It's as if the photon knows whether you're watching. We don't know how quantum entanglement works. When 2 particles are entangled, measuring one instantly affects the other, even if they're on opposite sides of the universe. Einstein called this spooky action at a distance and thought it meant quantum mechanics was incomplete, but experiments have confirmed it's real. We just don't understand how it works. You can create 2 entangled photons, send one to Tokyo and keep one in New York, and when you measure the one in New York, the one in Tokyo instantly responds, not after a light speed delay, instantly. This seems to violate the speed of light limit,
but it doesn't actually let you send information faster than light. You can't control what measurement you get, so you can't encode a message, but it's still deeply weird. We don't know if Schrödinger's cat is alive or dead until we open the box. This is a thought experiment about quantum superposition, but it raises real questions about how quantum mechanics applies to larger objects. In the thought experiment, a cat is in a box with a device that has a 50% chance of killing it based on a quantum event. According to quantum mechanics, until you open the box and observe, the cat is in a superposition of alive and dead. But that's absurd. Cats aren't in two states at once. Or are they? The question is, where's the line between the quantum world and the classical world? Atoms are definitely quantum. Cats are definitely classical. But where's the boundary? We can now create quantum superpositions of larger and larger objects, molecules, even tiny diamonds. How big can we go before quantum rules stop applying? We don't know. We don't know what the wave function actually is. In quantum mechanics, particles are described by wave functions, which give you probabilities of finding the particle in different states. But is the wave function a real thing, or just a mathematical tool? Physicists disagree. Some think the wave function is real. There are literally waves in some abstract space. Others think it just represents our knowledge about the particle. If it's real, what's it made of? Where is it? If it's just knowledge, whose knowledge? Does the particle have different wave functions for different observers? These questions don't have agreed-upon answers. Let me tell you something I've never said out loud before. I spent a year in college obsessing over quantum mechanics, trying to understand it, trying to make it make sense. I read every interpretation: Copenhagen, many worlds, pilot wave, relational quantum mechanics. I attended lectures. I did the math. And at the end of that year, I realized I didn't understand it any better than when I started. Not because I wasn't smart enough, but because nobody understands it. Richard Feynman, one of the greatest physicists of all time, said, "I think I can safely say that nobody understands quantum mechanics. If Feynman doesn't understand it, neither do I. And that's okay. Sometimes the universe is just weird." But Earth has its own share of weirdness, too.
Let's talk about Earth sciences, because there's a lot we don't know about our own planet. We don't know what's in the Earth's core. We've never been there. The deepest hole ever drilled, the Kola Super Deep borehole in Russia, only went about 12 kilometers down, and the Earth's radius is over 6,000 kilometers. Everything we know about the core is based on seismic waves and modeling. We think it's mostly iron and nickel, but we're not certain. The pressure and temperature at the Earth's core are so extreme that we can't recreate them in a lab. The core is as hot as the surface of the sun, about 5,000 degrees Celsius. The pressure is millions of times atmospheric pressure. We have no way to directly observe what happens under those conditions. We don't know exactly how the Earth's magnetic field is generated. We think it's caused by the motion of molten iron in the outer core, the geodynamo effect. Electric currents in the moving metal create magnetic fields, which cause more currents, creating a self-sustaining dynamo. But we don't understand all the details. And we don't know why the magnetic field occasionally flips. The north and south magnetic poles switch places every few 100,000 years. We know it happens because we can see the record in ancient rocks. Minerals aligned with the magnetic field when they formed, and we can read that alignment like a history book. But we don't know why it flips or when the next flip will occur. A magnetic reversal could be bad for us. The magnetic field protects Earth from solar radiation. During a reversal, the field weakens, potentially letting more radiation through. This could damage satellites, disrupt communications, maybe even affect life on Earth. Or maybe nothing bad would happen. We don't know. We don't know how many species exist on Earth. Estimates range from 5 million to over 30 million species. We've only identified and cataloged about 2 million. The vast majority of life on Earth is still unknown to us. Most unknown species are probably insects and microorganisms, but there are likely large animals we haven't discovered yet. In the past few decades, we've discovered new species of monkeys, deer, even whales. How do you hide a whale? The ocean is big. We don't know where lightning comes from exactly. We know it has to do with electrical charge separation in clouds, ice particles colliding and transferring charge. Positive charge accumulates in one part of the cloud, negative in another. When the voltage gets high enough, lightning. But we don't understand all the details of how it forms or why it strikes where it does. We can't predict exactly where lightning will hit. We can't even make lightning in a lab that's similar to natural lightning. We don't know how earthquakes work exactly. We know they're caused by stress building up in the Earth's crust and being released suddenly along faults, but we can't predict them. We don't know when or where the next big earthquake will hit. We can identify areas of high risk, places where stress is building up on known faults, but we can't say there will be an earthquake here next Tuesday. Seismologists have tried everything. They've monitored tiny tremors, looked for patterns, measured radon gas emissions, watched animal behavior. Nothing works. Some animals do seem to sense earthquakes before they happen. There are reports of animals acting strangely before major earthquakes, but we don't know what they're sensing, and it's not reliable enough to base predictions on. We don't know why ice is slippery. This seems like it should be simple, but it's not. For a long time, people thought ice was slippery because the pressure from your foot melts a thin layer of ice, creating water to slide on. But this doesn't fully explain it. Ice is slippery even when it's too cold for pressure to melt it. Ice skaters create less pressure than someone walking in high heels, yet they slide much more. The current best theory involves a quasi-liquid layer that exists on the surface of ice even below freezing, but we don't fully understand it. And that's the thing. We can't even explain why ice is slippery. Ice, frozen water, one of the most common things on Earth. Let's talk about physics, because even our most fundamental understanding of how things work has huge gaps. We don't know how to reconcile quantum mechanics with general relativity. These are our two best theories of physics. Quantum mechanics describes the very small, and general relativity describes the very large. But they're incompatible. They can't both be completely right. Quantum mechanics says that position and momentum are fundamentally uncertain. General relativity says that space-time is smooth and continuous. When you try to apply quantum mechanics to gravity, you get nonsensical answers, infinities that don't mean anything. We need a theory of quantum gravity that unifies them, but we don't have one. This isn't just an academic problem. There are situations where both theories should apply. Inside black holes, at the moment of the Big Bang, we can't describe these situations because our theories break down. It's like having a map of the United States that's blank in the middle because your two map makers couldn't agree on how to draw it. We don't know if string theory is correct. It's a candidate for a theory of everything that would unify all of physics. In string theory, the fundamental constituents of reality aren't particles, but tiny vibrating strings. Different vibration patterns correspond to different particles. It's mathematically elegant, but we can't test it. The energies required to test string theory's predictions are far beyond what we can produce in any experiment. We'd need a particle accelerator the size of the galaxy. So, string theory remains a mathematical idea that might be true, but might not be. It's been the dominant approach to quantum gravity for decades, but we're not really any closer to knowing if it's right. Some physicists are frustrated by this. Theories are supposed to make predictions you can test. String theory makes predictions, but they're untestable with current technology, maybe untestable forever. We don't know why there's more matter than antimatter in the universe. According to our understanding of physics, the Big Bang should have created equal amounts of matter and antimatter. These should have annihilated each other, leaving behind only energy. But somehow, there was slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. Those leftover particles are everything we see in the universe today. Why was there more matter? We don't know. This is called the baryon asymmetry problem, and it's one of the biggest unsolved problems in physics. If matter and antimatter had been created in exactly equal amounts, they would have annihilated and the universe would be nothing but light. No stars, no planets, no life. We exist because of this asymmetry, but we don't know why it exists.
We don't know what gravity is. We can describe how it works. Objects with mass attract each other according to Einstein's equations, but we don't know what causes it. We think there might be a particle called the graviton that mediates gravity, but we've never detected one. And we might never detect one because it would require insane amounts of energy. Every other force has a corresponding particle. Electromagnetism has photons, the strong nuclear force has gluons, the weak nuclear force has W and Z bosons, but gravity? We think it has gravitons, but we can't find them. Some physicists think gravity might not be a force in the traditional sense. It might be an emergent property of space-time, something that arises from deeper physics we don't understand yet. We don't know why the speed of light is what it is. Why is it 299,792,458 meters per second and not some other number? There's no explanation. It's just a fundamental constant of the universe. We can measure it very precisely, but we can't explain it. We don't know why the fundamental constants have the values they do. Things like the speed of light, the gravitational constant, the charge of an electron, these are just numbers we've measured. But why do they have those specific values? If they were even slightly different, the universe would be radically different and probably couldn't support life. If the strong nuclear force were slightly weaker, atoms wouldn't hold together. If it were slightly stronger, all the hydrogen in the universe would have fused into heavier elements, and there would be no stars. If the electromagnetic force were slightly different, chemistry wouldn't work the way it does, and complex molecules like DNA couldn't form. The constants seem to be fine-tuned for life. Why? Is it just coincidence? Is there a deeper explanation? We don't know. Some people invoke the anthropic principle. We observe these values because if they were different, we wouldn't exist to observe anything. It's a bit circular, but it might be the only answer we can give. Others think the multiverse might explain it. If there are infinite universes with different constants, we'd naturally find ourselves in one where the constants allow life. But we can't test that.
Let's talk about biology. Because even though we've mapped the human genome and understand a lot about how life works, there's still so much we don't know. We don't know why we have sex. Well, we know why, in an evolutionary sense, sexual reproduction creates genetic diversity. But it's actually a really inefficient way to reproduce. Think about it. With asexual reproduction, every organism can reproduce on its own. Every organism passes on 100% of its genes. Population can double with each generation. With sexual reproduction, you need to find a mate, which takes time and energy. You only pass on 50% of your genes. Half your offspring are males who can't bear children themselves. Population growth is much slower. So why do it? The main advantage seems to be genetic diversity. Sexual reproduction shuffles genes, creating new combinations. This helps populations adapt to changing environments and resist diseases. Parasites and diseases evolve to attack the most common gene combinations. Sexual reproduction keeps producing new combinations, staying ahead of the parasites. But the math is tricky. Does the benefit of genetic diversity really outweigh the costs? We're not entirely sure. We don't know how many genes we have. We can sequence the human genome, but deciding what counts as a gene is complicated. Early estimates said humans had over 100,000 genes. Then it was revised down to about 20,000 to 25,000. But there are stretches of DNA that sometimes act like genes and sometimes don't. There are genes that overlap with other genes. Counting is harder than it sounds. We don't know what most of our DNA does. We used to call it junk DNA because it doesn't code for proteins. But we've discovered that some of this junk actually has regulatory functions. It controls when and where genes are turned on and off. How much of it is functional and how much of it is actually junk? We're still figuring that out. Maybe most of it is junk. Maybe all of it does something. We don't know. We don't know how many neurons we have in our brains. The commonly cited number is 86 billion, but this is an estimate based on counting neurons in small samples and extrapolating. Actually counting every neuron is basically impossible.
The brain has roughly 100 trillion connections between neurons. Mapping all of them, creating a complete connectome, is one of the great challenges in neuroscience. We've mapped the connectome of exactly one animal, a tiny worm called C. elegans that has exactly 302 neurons. Even with just 302 neurons, mapping all the connections took years of work. The human brain has about 285,000 times as many neurons. We're nowhere close to mapping it. We don't know why humans are the only species that developed advanced language. Other animals communicate, birds sing, whales make complex sounds, bees do elaborate dances, but human language is way more complex and flexible. We can talk about things that don't exist, things in the past or future, abstract concepts, hypothetical scenarios. Why did we develop this ability and not other smart animals like dolphins or elephants? Some anthropologists think language co-evolved with social complexity. As our groups got larger, we needed better ways to coordinate and share information. Others think language might be a side effect of other cognitive abilities. We don't know for sure. We don't know why humans are capable of abstract thought and art. What evolutionary advantage does music provide? Why do we create art? Some people think it's a side effect of other cognitive abilities. Our brains evolved to solve practical problems, and art is just those abilities being applied in impractical ways. Others think art might have been important for social bonding or sexual selection. We don't know. Every human culture creates art. Every culture has music and dance and visual art and stories. It's universal, which suggests it's important somehow. But we can't say exactly what purpose it serves.
Let's talk about medicine, because despite all our advances, there's so much we still don't understand about the human body and disease. We don't know what causes most autoimmune diseases. We know the immune system is attacking the body's own tissues, but we don't know why it starts doing this. Type 1 diabetes, multiple sclerosis, rheumatoid arthritis, lupus. The immune system attacks different tissues in each disease, but we don't know what triggers it. Genetics plays a role. These diseases run in families. Environment plays a role. Rates have been increasing, but we don't know enough to prevent them or cure them. We can only treat the symptoms. We don't know what causes most mental illnesses. We have theories involving brain chemistry and neural circuits. Depression involves serotonin, schizophrenia involves dopamine, but these are oversimplifications. We don't fully understand depression, anxiety, bipolar disorder, schizophrenia, or other mental health conditions. Antidepressants work for some people, but not others. We don't know why. We can't predict who will respond to which medication. It's trial and error. Therapy works for some people, but not others. We don't fully understand how therapy works when it does work. Is it the specific techniques, or just having someone to talk to, or the placebo effect? We're not sure. We don't know how to cure most viral infections. We can prevent some with vaccines, but once you're infected, there's not much we can do except wait for your immune system to handle it. We have a few antiviral drugs, but they're specific to certain viruses and don't work as well as antibiotics work for bacteria. Why is it so hard to fight viruses? Partly because viruses evolve quickly, partly because they hide inside our own cells, making them hard to target without damaging the cells, partly because there are so many different viruses. But we don't have a general cure for viral infections the way antibiotics are a general cure for bacterial infections. We don't know how to cure cancer. We can treat it, surgery, chemotherapy, radiation, immunotherapy, but we can't cure it reliably. Cancer is really thousands of different diseases, each with different causes and characteristics. Lung cancer is different from breast cancer, is different from leukemia. Even two people with the same cancer might have tumors with different mutations that respond to different treatments. And we don't understand all the mutations. We can sequence the DNA of tumor cells and see thousands of mutations, but which ones are driving the cancer and which ones are just along for the ride? We don't always know. We're getting better at personalized cancer treatment, matching specific drugs to specific mutations, but we're still a long way from a cure. We don't know how some people live to 100 and others die at 60. Genetics plays a role, longevity runs in families, lifestyle plays a role, exercise, diet, not smoking, but we can't predict who will live how long with any accuracy. Some people smoke their whole lives and live to 100. Others eat healthy, exercise, and die young of cancer or heart disease. Why? Bad luck? Genes we haven't identified yet? Environmental factors we don't understand? We don't know. We don't know how to stop aging. We can slow it down, maybe. Eat healthy, exercise, don't smoke, manage stress, but we can't stop it or reverse it. Some scientists think aging might be a disease we can cure, but we're nowhere close to that yet. The problem is that aging isn't one thing. It's accumulating damage, DNA damage, protein damage, cellular damage. It's cells that stop dividing. It's stem cells that get depleted. It's the immune system getting weaker. It's 100 different processes all degrading at once. To stop aging, we'd have to fix all of them. And we don't even fully understand all of them yet. But here's what really fascinates me, the questions we can't even ask yet. Let's talk about consciousness again, because it's such a fundamental mystery. We don't know if consciousness is unique to biological brains or if it could exist in other forms. Could a computer be conscious? Could an AI? How would we even know? This is called the hard problem of consciousness, and it's not just about understanding the brain. It's about understanding the relationship between physical processes and subjective experience. Even if we completely mapped the brain, even if we knew exactly which neurons fire when you see red, we still wouldn't know why those neurons firing creates the experience of redness. Some philosophers have proposed the idea of philosophical zombies. Imagine a being that looks and acts exactly like a human but has no inner experience, no consciousness, no subjective experience, just programmed responses. Would this zombie be distinguishable from a regular human? If not, how do you know everyone around you isn't a philosophical zombie? How do you even know you're not a zombie yourself, just programmed to think you're conscious? We don't know if animals are conscious in the same way humans are. We know they have brains and nervous systems. We know they respond to stimuli. But do they have subjective experiences? Does it feel like something to be a dog, or a bird, or a fish? We can't ask them, and we can't get inside their heads. Some animals probably are conscious, mammals and birds at least, given the similarity of their brains to ours. But fish? Insects? Where's the line? Is a fly conscious? A worm? A bacterium? We don't know. We don't know if consciousness can exist without a brain. Some people believe in souls or spirits that exist independently of the body. Others think consciousness is purely a product of brain activity. When the brain dies, consciousness ends. We have no way to test this scientifically. Near-death experiences suggest consciousness might continue after the brain stops, but they could also just be hallucinations produced by a dying brain. We can't know. Let's talk about language and thought, because the relationship between them is mysterious. We don't know if language shapes thought or if thought shapes language. This is called the Sapir-Whorf hypothesis, or linguistic relativity. Do people who speak different languages actually think differently? Some studies suggest yes. For example, some languages have different words for different shades of blue, and speakers of those languages can distinguish them more easily. Russian has separate words for light blue and dark blue, and Russian speakers can distinguish them faster than English speakers. The Himba people of Namibia have more words for different shades of green and can distinguish them better. But how much does language really affect thought? Can you think thoughts you don't have words for? Probably yes. Artists and musicians express things that are hard to put into words. Babies think before they learn language, but language might still shape and constrain thought in ways we don't fully understand. We don't know how children learn language so quickly. A 3-year-old can speak in complete sentences with complex grammar, even though no one explicitly taught them the rules. Noam Chomsky proposed that humans have an innate language faculty, a universal grammar hardwired into our brains.
Kids don't learn language from scratch, they're born with a template, and they just fill in the specific details of whatever language they're exposed to. But we don't know if this is true or how it would work. Where in the brain is this universal grammar? What does it consist of? Different languages have very different structures. How universal can the universal grammar really be? We're still figuring this out. We don't know how language evolved. Did it develop gradually from animal communication systems, or did it emerge suddenly as a unique human ability? We don't know. There's no fossil record of language. Words don't fossilize. We can only make educated guesses based on indirect evidence. Some researchers think language might have started with gestures and only later become vocal. Others think it started with vocalizations and gestures came later. We don't know when it happened either. Maybe 100,000 years ago, maybe 2 million years ago. The only clear evidence is that by 50,000 years ago, humans were creating complex art and tools, which suggests they probably had complex language.
Let's talk about mathematics, because even though math seems like the most certain kind of knowledge we have, there are deep mysteries there too. We don't know if math is discovered or invented. Do mathematical truths exist independently of human minds, waiting to be discovered? Or do we create math as a useful tool for describing the world? Most mathematicians lean toward the discovery view. It feels like math exists out there somewhere, and we're just finding it. The same theorems are proven by different people in different cultures. 2 plus 2 equals 4 regardless of whether humans exist to count. But some philosophers argue that math is invented. It's a language we created, a useful fiction for describing patterns we see in the world. Here's a concrete, unsolved problem. We don't know if there are infinitely many twin primes. Twin primes are pairs of prime numbers that differ by 2, like 11 and 13, or 17 and 19. We think there are infinitely many twin primes, but we haven't proven it. This has been an open problem for over 2,000 years. In 2013, a mathematician named Yi-Tong Zhang made a breakthrough by proving that there are infinitely many pairs of primes that differ by at most 70 million. That sounds like a lot, but it was a huge step toward proving the twin prime conjecture. Other mathematicians refined his work and got the number down to 246, but we still haven't proven it for 2. We don't know if the Riemann hypothesis is true. This is one of the biggest unsolved problems in mathematics. It's about the distribution of prime numbers, and proving it would have huge implications for number theory and cryptography. The Clay Mathematics Institute is offering $1 million to anyone who proves it. Mathematicians have been trying for over 150 years. Computers have verified it for the first 10 trillion cases, but we still don't have a proof. We don't know if P equals NP. This is a fundamental question in computer science and mathematics. Roughly, it's asking whether problems that are easy to check are also easy to solve. For example, if someone gives you a completed Sudoku puzzle, it's easy to check if it's correct. But is it also easy to solve a Sudoku puzzle from scratch? Most computer scientists think the answer is no. P does not equal NP. Some problems are inherently harder to solve than to check, but we haven't proven it. The Clay Mathematics Institute is offering another $1 million for a proof, either way. These aren't just abstract puzzles. If P equals NP, it would revolutionize computer science. It would mean lots of problems we think are hard, like breaking encryption, optimizing complex systems, solving protein folding, would actually be solvable efficiently. It would change everything. But we're pretty sure it's not true. We just can't prove it. Let's talk about the future, because obviously we don't know what's going to happen, but there are specific things we're uncertain about that really matter. We don't know if humans will survive the next 100 years. Climate change, nuclear war, pandemic, asteroid impact, AI gone wrong, there are lots of ways civilization could collapse or even go extinct. Will we make it through? Probably. Humans are adaptable. We've survived ice ages and volcanic eruptions and plagues, but probably isn't certainly. The risks we face now are different from historical risks. Nuclear war could kill billions in hours. An engineered pandemic could be worse than anything nature has created. Climate change could make large parts of the Earth uninhabitable. We're in uncharted territory. We don't know if we'll ever colonize other planets. We have the technology to reach Mars, but could we actually live there permanently? Mars has no breathable air, no magnetic field to protect from radiation, gravity only 38% of Earth's. Could we terraform it, make it Earth-like? We don't know if it's possible or how long it would take. Estimates range from hundreds to millions of years. And even if we could terraform Mars, should we? Mars might have microbial life in subsurface water. If it does, would we be committing genocide by terraforming it? Do we have the right to alter an entire planet? These are ethical questions we'll need to answer if the science ever gets there. We don't know if we'll ever achieve nuclear fusion as a practical energy source. We've been 30 years away from fusion power for the last 70 years. Fusion is what powers the sun, smashing hydrogen atoms together to make helium, releasing enormous energy. It's clean, safe, and uses fuel that's essentially limitless. But it's really hard to do. The problem is containing the plasma. You need to heat hydrogen to millions of degrees, hotter than the sun's core, and keep it stable long enough for fusion to occur. We can do it for seconds, but we need to do it for hours or days to generate useful power. Will we ever actually do it? Maybe, but we don't know. We don't know if we'll ever cure aging. Some scientists think it's possible in principle. Others think aging is too fundamental to life to ever be stopped. The optimists point to organisms that barely age and argue we could apply those principles to humans. The pessimists point out that aging is hundreds of different processes and fixing all of them might be impossible. But even if we could cure aging, should we? If people stopped dying of old age, population would explode, resources would run out, society would stagnate, same people in power forever, no new ideas. Maybe mortality is necessary for progress. These are questions we'll have to grapple with if the science ever gets there. We don't know if we'll ever make contact with alien life in the next century. It could happen tomorrow, or it could never happen. We're listening with radio telescopes, we're looking for signs of life on exoplanets, we're sending messages into space, but we don't know if anyone is out there or if they'd want to talk to us if they are. And if we do make contact, what would happen? Would it be peaceful or hostile? Would they share knowledge with us or study us like lab animals? Would they even be comprehensible to us, or would their mode of thinking be so alien that communication is impossible? We're assuming aliens would communicate with electromagnetic radiation, but maybe they use something completely different. We might be having a conversation with them right now and not even know it. Let me bring this all together, because we've covered a lot of ground, and I want to make sure you understand the point. The point isn't that knowledge is impossible, or that we should give up trying to understand things. The point is humility. We're constantly working with incomplete information. Our senses can deceive us. Our logic can fail us. Our theories might be wrong, but that's okay. That's how science works. We make our best guess based on available evidence, and then we test it. When we're wrong, we adjust and try again. We get closer to truth even if we never quite reach it. And there's beauty in mystery. There's excitement in not knowing. Every question without an answer is an opportunity for discovery. Every gap in our knowledge is a chance for someone to make a breakthrough. Think of human knowledge like a sphere expanding into the darkness. The more the sphere grows, the more we learn, the larger the surface area becomes. And the surface is where the sphere touches the unknown. So the more we know, the more we become aware of what we don't know. The sphere of knowledge grows, but so does the boundary of ignorance. Or here's another way to think about it. Imagine you're in a dark room with a flashlight. The flashlight is your knowledge. You can see what's in the beam clearly, but the room is huge and there are countless things in the darkness beyond your light. As you move the flashlight around, you illuminate new things, but you also see glimpses of other things further in the darkness. Every answer raises new questions. We don't know why we yawn or laugh or dream. We don't know how to measure coastlines or what's at the bottom of the ocean. We don't know how life is or where it came from. We don't know if we're alone in the universe or why aliens haven't contacted us. We don't know what most of the universe is made of. We don't know what time is or why it flows forward.
We don't know how consciousness works or if we have free will. We don't know how to cure aging or cancer or the common cold. We don't know if P equals NP or if there are infinitely many twin primes. We don't know if we're living in a simulation. We don't know if this is the only universe. We don't know what happened before the Big Bang or what will happen after the heat death of the universe. We don't know if time travel is possible or if there are extra dimensions we can't perceive. We don't know why the laws of physics are the way they are or if they could have been different. And you know what? That's okay. Because the beautiful thing about not knowing is that we can find out. Maybe not today, maybe not in our lifetimes, but eventually. Someone will figure out why ice is slippery. Someone will prove the Riemann hypothesis. Someone will understand consciousness. Someone will answer these questions. And when they do, they'll raise new questions we can't even imagine yet. Questions about things we don't even know exist yet. And that's the real beauty of it. The journey of discovery never ends. There's always more to learn, always more to explore, always more to understand. We used to think we understood everything. Ancient Greeks thought they had it figured out. Medieval scholars thought they knew how the world worked. Victorian scientists thought physics was almost complete. They were all wrong. And we're probably wrong too about lots of things. Future generations will look back on our certainties and laugh. But that's progress. That's growth. That's how we move forward. I used to think that uncertainty was something to fear, something to overcome, but I've learned to embrace it. Not knowing doesn't mean we're stupid or failing. It means we're humble enough to recognize the limits of our understanding. It means we're curious enough to keep asking questions. It means we're brave enough to admit we might be wrong. And honestly, would you really want to live in a world where we knew everything? Where every question had been answered, every mystery solved? That world would be boring. The unknown is what makes life interesting. It's what drives us to explore, to discover, to create. So the next time someone asks you a question and you don't know the answer, don't be embarrassed. Don't make something up. Just say, I don't know. And then maybe add, but let's find out together. Because at the end of the day, we're all just stumbling around in the dark, trying to make sense of a universe that's far stranger and more wonderful than we ever imagined. We don't know where we came from or where we're going. We don't know what we are or why we're here. We don't know what happens when we die or if any of this means anything at all. But we're here anyway, asking questions, seeking answers, pushing back the darkness one small discovery at a time. And that's something. That's everything, actually. We don't know everything. We probably never will. But that's what makes life worth living. The search for understanding, the joy of discovery, the thrill of finally answering a question that plagued humanity for centuries. That's what we're here for. So keep asking questions, keep searching for answers, keep wondering about the world around you. Because the day we stop asking questions is the day we stop being human. And we're not there yet. Not even close. There's still everything we don't know.